Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everybody. How's everybody doing? Hopefully everyone have a good weekend. Good, good. Yeah, that's good. Yeah, hopefully, this morning was a bit cooler, so hopefully, that trend continues and we finally see some fall and winter weather. Yeah, week 9, it's crazy. It's always surprising how fast the semester goes, but at the same time, it's still very exhausting. Okay, so the plan for today is we're going to start a new set of lecture notes. So it's kind of the sequel to what we did last week. So actually, what we did last week was there was almost no finite elements in that at all. It was basically just math. But this week, what we're going to see is we're going to build off what we did last week and to see how we can actually get finite element problems and finite element formulation from that. Okay. And so before I start, I do want to talk about the midterm just briefly. And so I finished graded those on Thursday, so you should be able to see your scores. So I tried one of the new features in Canvas where I put comments directly onto your PDF because I thought that would be more useful than kind of just reading the comment box on the side, because then you can see exactly where I'm giving you feedback and stuff like that. So was everyone able to go onto Canvas and read the comments that I left you on there on your exam? Great, great. Okay, yeah, so that's working well. So I'll probably start using that for the homeworks as well, because I was using the comment box just because I knew that you guys would be able to see that. But if the comment thing works, I think I'll probably start using that, because I think that's a little bit more useful, just because then I can kind of point it out. So it's almost the same thing as if you guys turned in the homeworks by hand and I kind of circled things for you on there. So it's kind of the same thing. So to statistics, so the average on the midterm. Let me just check the numbers again just to make sure. So average on the midterm was about a 42 out of 50. Okay. So about an 84%. Right. So that's pretty good. I mean, that's of course it's a little bit higher than normal, but we are in a virtual environment, and there was 24 hours for the exam. So I did write the exam under the assumption that you would have MATLAB to help you with the problem. So an exam like that, I think definitely it would be really difficult to do in class, especially with all the calculations that were involved. But I think with the virtual environment, I think that it kind of helped to I think give a more complete exam over everything that we've covered on that first section. But all things considered, I think this is a good average, and you guys did really well. So I was really happy with that. Are there any questions just in general about the exam? If you have individual questions about kind of the feedback or your grade, I'm happy to answer those. But probably email or Discord might be a little bit easier for that too. So the question is, will the final also be 24 hours? So right, so we're not going to have a final exam, so we're going to have a final project instead. But there will be another midterm exam. So there's going to be one more midterm. I think we have it scheduled for after the Thanksgiving break, and that will also be a 24-hour exam. Mm-hmm. Yeah, so the final project, I think we'll have it due probably the Monday after finals week. I don't know if I've set a date yet, but we'll have it due after finals so that you guys can focus on your other classes and other exams without having to worry about the project. Yeah, so there's going to be 2 midterms. Yeah, so there are one first half midterm and one second half midterm. So the next question is the second midterm cumulative? So it will not be cumulative. So it'll basically, the starting point for the second exam will be, what we started covering last week, which is the strong and weak forms. And then it's going to continue on with the finite element form. So because, this kind of second part of the class is quite different from the first half. I mean, it's all still finite elements, but, the theory is quite different. So, the midterm is not going to be cumulative. So it's going to be it's just going to cover the stuff after the midterm. The question is, what does the final project consist of? So the final project, it'll be, you can kind of think of it as kind of an accumulation of all the MATLAB stuff that we're going to be doing. So you guys just turned in kind of our first big kind of MATLAB assignment, on Sunday, which was kind of a MATLAB implementation of all the finite element stuff that we've been doing in the first half. And so starting now, we're going to start working on how do we implement this kind of theory into MATLAB. And then for the final project, what you're going to do is it's going to be a 2D finite element code on an arbitrary mesh. And so basically what I'm going to have you do is I'm going to have you explore some of the meshing options within MATLAB, because MATLAB has some cool functions to basically take a shape and then break it up into any kind of shape that you want. And then I want you guys to implement a code that can run a finite element simulation onto that. Okay? So we're basically going to be building up towards that. So you know, everything that we're going to be doing this week and over the next couple of weeks will be kind of, you know, a big part of that final project. Yeah. All right. Any more questions before we get started today? Okay. So let's go ahead and get started. So the topic for this week is finite element formulations. Okay. And so in particular, you know, what this unit is going to cover is, you know, how do we take, you know, a boundary value problem like what we talked about last week, strong form, weak form, and then actually turn that into, you know, something that we can do with finite elements. Because up to this point for the class, you know, we've been doing finite element problems, but they're mostly just structural problems. So what we're going to be learning this week is how do we take like a mathematical boundary value problem and turn it into finite elements. Okay. And so our starting point is actually going to be the weak form. Okay. And so if you remember, the weak form, you know, it has nothing to do with the you know, the superiority of one form over the other. But the reason the weak form gets its name is because it has weaker weaker continuity requirements. Okay? And so remember, the big thing that was based off of was the fact that the weak form, instead of having a second order derivative, the weak form only has first order derivatives. Okay? And remember, the way that we obtained this from our boundary value problem was we performed integration by parts. And with integration by parts, that basically allowed us to move some of the derivatives, mostly from the solution term over to our weighting function, right? And so remember, the big thing about the weak form is that we had this weighting function, and that kind of lets us soak up one of the derivatives. Okay. And so what we did actually at the end of last week, which is going to be, you know, it's going to be crucial for what we do this week, is we learn how to find approximate solutions. Okay. Right. And so this is really significant in that, you know, it's almost like kind of a new way to solve these kinds of differential equations, where we're not solving the equations directly, you know, by integrating. But remember, the way that we obtained approximate solutions was that we had to assume that we knew what the solution looked like. Okay. Right. And so I think in the last example that we did at the end of last week, we assumed that our solution was a quadratic function. And so it was a0 plus a1x plus a2x squared. Okay. And then after we assumed a form of the solution, what we did was we computed the optimal values for the coefficients that made our approximate solution as close as possible. Okay. Okay. And so I wanted to kind of recap that and from last week, because that's, you know, that's going to be kind of the motivation for how we actually do this for finite elements. Okay? Because for finite element formulations, we're going to basically follow the same format, but instead of you know, finding a weak solution or an approximate solution that's valid over an entire domain, instead what we're going to be doing is finding an approximate solution that's only valid over an element. Okay. And so, what we're going to be, what you're going to see this week is, if you kind of go back for our very first lecture about, what are the kind of the general steps to a finite element, analysis, we're going to be giving a lot more meaning to kind of those first two steps. If you remember those first two steps, the first one is just discretize. And so we have to take our domain into, and that means breaking up into elements. Okay? And so we're going to be starting for a 1D case. So let me kind of draw a picture for what that means. Okay. And so for a 1D case, our full domain just looks like this. So it's not that exciting. It's just a line. Okay. But when we discretize, okay, we're going to take this line, and then we're going to break it up into lots of smaller baby lines. Okay, where each of these segments right here, these are our elements. Okay, and then on the other hand, all these dots right here, these are going to be our nodes. Okay, and so the process of discretizing is that we're going to take our full geometry, which in 1D is just going to be a line, and then we're going to break it up into a lot of smaller geometry. So in this case, it seems really trivial and kind of almost silly to break up one big line into smaller lines. But I want you guys to always kind of be thinking about how this is going to apply to 2D and to 3D. Okay, and so even if for 2D, right, you can kind of think of lots of different complex shapes that you can have in 2D. And so discretizing, that means breaking up a complex 2D shape into a bunch of simpler 2D shapes that you can more easily solve. So we're going to be starting with 1D just because the theory and the math is a lot easier for 1D. But I want you guys to always be thinking of how would this be applied in multiple dimensions. Okay. Okay. Any questions on this? Okay. Okay. And so now how do we actually find a solution for this? So, I'm going to do kind of the same dichotomy here. So, on the left here, I'm going to say what we would do for the full domain. And on the right here, this is for, finite elements. Okay, so for the full domain problem, if you remember kind of our last example from last week, we would solve for the solution. So let's say that our solution is given by u of x. Okay. And then we would solve for basically one function that would span that entire domain. Okay. All right, so say that our domain has length L, and so over that domain from x is greater than or equal to 0 and less than or equal to L, we're going to be solving for one function that encapsulates the entire solution. So we have one u of x is equal to a0 plus a1x plus a2x squared. Okay. But for finite elements, we're going to modify this a little bit, which it might only seem like a superficial change at first, but we're going to be doing this. Okay. Okay. And so for finite elements, we're going to be solving, we'll say that we're going to solve for a quadratic function again, but instead of solving this over the entire domain, this solution right here is only going to be valid over a single element. Okay. 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 And so what we're going to do is we're going to have basically a function like this for every single element in our domain. Okay. Okay. And then once we've done that, we're going to basically just add them all together, or basically stitch them together. And this is what's called a piecewise approximation. Okay. Because we're not just doing one global approximation for the entire domain, we're going to be doing lots of small approximations on, just slices our domain, and then piecing them all together at the end. Okay. Okay. And so that's the general idea with this finite element approach, where instead of trying to find one solution that covers the entire domain, we're going to find lots of small solutions on each of the different elements, basically solve the same problem over and over again with different different element coordinates, and then just stitch them all together at the end. Okay. And then by that nature, again, when you're applying this to kind of higher dimensions, 2D and 3D, this makes solving those problems easier, because if you solve kind of a really complicated partial differential equation, that's a lot easier to do on a much smaller shape that the shape of, like maybe a triangle or a square, than it is to find it over an entire entire bracket or entire bike ring or something like that. Okay, and so before we actually start, deriving, what does these look like, we need to talk about some of the requirements, because, this idea of solving all these tiny problems and then stitching them together at the end, we need to make sure that, we follow some rules just to make sure that we get a solution that actually makes sense. Okay. Okay, so these are some of the requirements for our finite element solution. Okay. Okay, so the first requirement that we're going to talk about is this continuous requirement. Okay, so because we're solving, you can almost think of it as we're solving individual problems on each of the different elements. They have to form a picture at the end, right? So you can't just say solve all these problems just individually, and then if you do that, then they're not going to form a nice picture at the end. Okay, and so the way that we say this mathematically is that our total solution, after adding up all the elemental contributions, it has to be continuous across element boundaries. Okay, and so you can't have one solution from one element, that's going like this, and then in the other element it might be going like this. So that can't happen. So basically, the solution has to be kind of contiguous as you go across the elements. Okay, and I'll draw an image of that, of what that looks like. Actually, I can do it right here. We have some space right here. Okay. And so say that we have a domain that looks like this. So I'm just going to do 2 elements for now. Okay, so we'll call this element A and element B. Okay. In red right here, I'm going to draw the solution. So if you have a situation that looks like this, where over one element the solution looks like that, but then as soon as you jump to the next element, and then the solution starts looking like this. Okay. Or in other words, there's this gap right here. Okay. This can't happen, and so you can't have a situation where as you go from element to element and your solutions are jumping, because that doesn't make any sense at all. Okay. And so what you need to have instead is something that looks like this. Okay. So we have 2 elements, A and B. If we have the solution from A, look something like this. Okay. And so across A, our solution starts here and then ends up right here. And then once we enter element B, the solution has to pick up from the exact same spot. So it has to be right here. It has to be like that. Okay. Right. And so how do we actually impose this this requirement here? And so the way that we impose this is that every element has to have a neighbor, right? And the neighbor, the way the elements neighbor each other is they share a common node. Okay. And so if we consider 2 elements that share a node, like we have right here, okay. And so what we're going to enforce is that when 2 elements share a node, that the solution at the node has to be the same. Okay. And so I'm going to keep the language here general by saying, you know, all elements that neighbor a node, that border a node, you know, have to have the same solution. For the 1D case, you know, we can only have 2 elements that border a node, but once we get into 2D and 3D, you know, this actually grows quite a bit. You might have 3, 4, 5, 6 elements that all border a node, and then they all must have the same nodal solution. Okay, and so what this means for our systems is that, you know, we're going to have a situation similar to, you know, what we had for the first half of the class, where, you know, when we're solving our global linear system, what we're going to be solving for actually are these nodal solution values right here. Okay, and so it might, you know, these problems might look different than before, but, you know, we're still going to be solving for the nodal solutions. Okay, and by doing that, we basically guarantee that as we go across the elements, then the solutions are always going to be continuous. Okay. All right. Any questions on this? Okay. Okay. So that's the requirement for the solution as you go across elements. Okay. But there's also some requirements for the solution within the elements too. Okay. Okay. And so the first requirement that we'll talk about, you know, has a similar name as the previous one, but it has kind of a slightly different meaning, and that's the idea of continuity. Okay. And so what this basically means is that, you know, just like across element boundaries, you know, when you're going inside the element, the solution also has to be continuous. Okay. And so that seems, you know, pretty straightforward, but it's a little bit, but the way that we apply this and the way that we, you know, actually impose this on our finite element solution is actually going to be a little bit different than the previous case. Okay, because for these cases, when we're inside the elements, the behavior of the solution is driven by the weak form. Okay, so in particular, you know, the driving factor for our continuity is going to be the highest order derivative in our weak form. Right? And so let's say that if we have a weak form and k right here, so k is an integer, k is the highest order derivative in the weak form. Okay. So, you know, for the examples that we've done before, which is just elasticity and heat transfer, you know, k is going to be 1, and because in our weak form, our highest order derivative is just 1. Okay. And so if k is the highest order derivative, then what we require is that our approximation functions, or our approximate solution, the derivative of it, or the approximation functions have to be continuous up to the k minus 1 derivative. Okay. And so, you know, for the basically what you need to do is you basically just say, you know, if k is our highest order, which is just 1 in this case, that means that our function needs to be continuous up to the k minus 1 derivative. Okay. And so if we take, you know, just one derivative of our solution, or in this case, we take 0 derivatives of our solution, then our function has to be continuous over there. Okay. And so as an example, you know, In our case, we have, you know, first order derivatives in our weak form. Okay. Then our approximation only has to be continuous in the function value. Okay. And so, you know, if we take, basically what that means is if we take one derivative of our approximate solution, then it just has to be a constant. Okay, so it can't be zero. Okay, and so the lowest order function that can satisfy this is a linear function. Okay. And so if we have UE is equal to A0 plus A1x, okay, if we take one derivative of this, okay, then we're just left with A0 or A1, sorry. Okay. And so if, you know, our derivative here is A1, which is a continuous function, you know, it's just a constant, but a constant is still a continuous function, then we're okay, you know, for our, this satisfies a requirement, okay? Because if you can imagine it, you know, if we look at our weak form and say that our approximate function here was just a constant, so we just said A0, okay? If we take the derivative of this, we just simply get 0, right? And so if we plug in 0 into our weak form, you know, that's not going to work because we're not going to be able to find a solution for that. Okay? And so, you know, another way to basically state the continuity requirement, which kind of makes more sense to me in my head, is that when you take derivatives of this function and plug it into the weak form, you have to get something that allows you to actually solve for a solution. You have to get something that makes sense. Okay? And so if you plug in, if you take a derivative, if you take, you know, all the derivatives that you need to, and then plug it into the weak form, and then all you get are zeros, then, you know, that's not going to satisfy the continuity requirements. Okay. Okay. And so this kind of example right here, which is the one we're going to be working with, has a kind of a more mathy term, and the mathy term for this is called C0 continuity. Okay. And so if you look, if you read kind of finite elements textbooks, and then they talk about just C0 continuity, C1 continuity, that's basically what it means. So C0 continuity just means that if you take the derivative once and you get a constant function that's something that's continuous, you know, then you're good to go. Okay. All right. Any questions on this? And so, you know, this continuity requirement is basically the reason why we went through that whole, you know, integration by parts thing to lower the order of the derivative. Okay? It's basically so that we can relax our continuity requirements. Because if we had a second order derivative, you know, we'd have to go up one level in our function, and that, you know, adds actually a lot of complications. Okay, and so that's continuity. So that's kind of the big and important one. So the next one we have is completeness. Okay. And so the completeness requirement just basically states that, you know, if we're going to, you know, for all the things that we're going to consider here, we're just going to have just polynomials, okay? And so if we have to, you know, go up to a, you know, say a kth degree polynomial, okay? Okay. And so say that we have to go to like a third order polynomial or second order polynomial. And then what this basically says is that, you know, our polynomial has to be complete. Okay? And so what that means is that we have to include basically all of the lower order terms up to that kth order. Okay? And so as an example, let's say that, you know, we need a quadratic function. Okay. Okay. And so if we need a quadratic function, you know, one valid thing for this would be to include all the terms that are lower than this. So that includes the constant term, a0, the linear term, which is a1x, and the quadratic term, which is a2x squared, okay? And so this is a complete polynomial because it includes all of the different terms, okay? What we can't do is, let's say that, you know, say that we didn't like the linear term for whatever reason, okay? They said something mean to you someday, right? But you can't just leave it, you can't just not invite him to the party. So, you know, we can't just leave off the linear term because then this polynomial wouldn't be complete, okay? And so I don't want to get too much into the completeness requirement because that gets into kind of the heavy math of, you know, convergence of finite elements. But basically, if you don't have a complete polynomial like this, then it's really difficult to get convergent, or it's impossible to guarantee convergence of your finite element. Okay. All right. Any questions on this? I'm gonna go turn on the lights for just for a few seconds. Okay. Okay, so those are the requirements. And so now let's actually get into deriving our element stiffness matrix. Okay? And so up to this point, you know, we've already discretized our domains. We've basically broken up our elements into our domain into elements. Okay? And a nice fun thing for you know, for these from now on is that, you know, the discretization or how many elements that you want, that's mostly going to be up to you guys now. So, you know, for all the stuff that we did for the first midterm, you know, how many elements, how many nodes, that was kind of basically fixed based on whatever problem that you were solving. You know, but for these problems, you know, and especially for your project, how you discretize the domain is really going to be up to you guys, okay? Except for when I tell you that it's not. And that's, you know, when we're doing homeworks and I want everyone to get the same solution. Okay. But in reality, you know, you saw that in ANSYS too, where, you know, when you're meshing your domain, when you're discretizing it, all those parameters are up to you. You know, it depends on how much cost and how much you know, accuracy you want in your solution. Okay. All right. So the next thing that we're going to go over is that now that we've established the requirements, is to how do we actually, you know, turn this into a finite element problem. And to do that, we need to go over something called shape functions, right? And so this is basically going to constitute step 2 of our, you know, general finite element process, where, you know, this is kind of the step that I think has been most nebulous up to this point, which is assume a functional form. Okay, and so for this, you know, I think it's probably most useful to kind of work through kind of one of the simpler cases, just to kind of show you how it's done. Okay, so say that we have our 1D element right here, and say that we have a 2D or 2-node element. Okay. Okay. And so we know a couple things about these nodes. And so first thing that we're going to know is that we know the coordinates for these nodes. So that's going to be x1, x2. So you can kind of think of that as kind of the distance along the x-axis for this. And we also know the nodal solution values. Right? And so one of them, you know, the top parts there, that's going to be the solution to our boundary value problem at the nodes. And on the bottom, there's just simply the geometric information about where these nodes are located. Okay. And so for this, you know, for this situation, we're basically going to use the simplest function that we can use in our weak form, where we're going to assume a linear function. Okay. And so our linear function will look like this. And so we have here, what we have here is a complete linear polynomial. So we have our constant term and our linear term. And in this expression, we have 2 unknowns. And so first of all, we have A0 and then we have A1. Okay. And so the next part is we're going to solve for the values for A0 and A1 that will give us kind of the most optimal solution in this case. Okay. All right. Any questions on this? Okay. Okay. And so based on our requirements for our finite element solution, remember that the nodal solution values have to be matched within the element, right? And that's to basically ensure that, you know, what we get in this element will be kind of consistent with what we get on its neighbor, okay? And so the way that we're going to impose this requirement is, let's enforce that the that our approximate solution UE, okay, let's enforce that our approximate solution matches the nodal values at the extremities of our element. Okay. Okay. Right. So what we're going to do is we're going to set up a system of two equations for our two unknowns, right? Because we have two coefficients that we want to solve for, and so we need two equations in order to solve it. Okay. And so first, let's enforce that our approximate solution matches the nodal solution at node 1. Okay. And so that's going to give us UE at x1. Remember, so x1 is the coordinate of the left node. Okay. Right. And so if we plug in x1 into our expression, we get a0e plus a1e x1. Okay. And this has to equal to u1. Okay, because that's the nodal solution over there. And then similarly at x2, when we evaluate that approximate solution at x2, then this has to equal to u2. Okay, and so now what we have here are two equations for our two unknowns, and we can basically solve them for a0 and a1. Okay, so unfortunately, you know, I know that there's some symbolic packages in MATLAB that can do this, but you know, let's do this by hand. Okay, and so first thing I'm going to do is I'm going to subtract these two equations. Okay, and by subtracting them, I can get rid of a0e. Okay, and so if I do that, then I get a1e x1 minus x2. Okay, and this is equal to u1 minus u2. Right, and so if we solve this equation for a1, what we get is u1 minus u2 all over x1 minus x2. Okay. And so that's our first constant. And so what we can do now is we can plug this back into either of these equations and solve for a0. Okay. And so let's plug it back into this top one. Okay. And so we have I'll use a different color. Use blue. Okay. And so from this we have a0 e plus u1 minus u2 all over x1 minus x2, okay, times x1 is equal to u1. Okay. If we solve this expression for a0, what we get is x1 u2 minus x2 u1 all over x1 minus x2. Okay. And so if we plug in our a0 and a1, we get the following. Okay. So we get ue of x is equal to x1 u2 minus x2 u1 all over x1 minus x2 plus u1 minus u2 all over x1 minus x2 and then x. Okay. And so with this approximation function is a linear function that will allow us to match the nodal solution value. So this function right here basically satisfies all the requirements for our finite element solution. Okay. All right, any questions about how we got here? Okay. Okay. And so, you know, that approximation function is fine the way it is. But what I'm going to do now is I'm going to basically rearrange this a bit to make it a little bit easier for our calculations later. Okay. Okay. And the way I'm going to rearrange it is I'm going to rearrange it into a way such that we get u1 times something plus u2 times something. Okay. Okay. And so if we do that, we get the following. Okay, so we get ue of x is equal to u1 times the quantity x minus x2 minus over x1 minus x2. Okay. Plus u2, and then this is times the quantity x1 minus x all over x1 minus x2. Okay. And so I put this in this form for a very special reason. Okay. Because what I have in the parentheses right here are very special functions, and that we call these guys shape functions. Okay. And so shape functions are typically given the symbol big N. Okay. And so on the left-hand side, because it's the shape function associated with u1, we call that n1. And on the right side, since that's the shape function associated with node 2, we'll call that n2. Okay. And so with these shape functions, we can kind of rewrite our function for ue. And so ue of x is going to be u1 n1 of x plus u2 n2 of x. Okay. All right. And so as you can imagine, because it's the title of this section, you know, these shape functions are going to have some very you know, important. They're going to have some important duties. Okay. Okay. And so, you know, the way that we got this, you know, this function right here was to basically, we assumed a form for a solution, right? So we assumed our solution was a linear function. And then we solved for the best coefficients a0 and a1 that made our approximate solution basically satisfy our requirements, okay? And then we ended up with this function right here with the shape functions. Right? And so, you know, this is our expression for the approximate solution, but it also has another purpose too. And the purpose is to interpolate. Okay? And so this function is also sometimes called the finite element interpolation function. Okay? Because what is the purpose of interpolation? So interpolation is basically, you know, it's basically the act of solving for the solution value at a location where you don't know for sure. Okay? And so in this particular case, you know, we know, or we're going to solve for the solutions at, you know, the nodes of our elements, right? So we're going to solve for u1 at node 1 and u2 at node 2. And so what the interpolation function is going to allow us to do is to basically solve for the solution values at any other location in the element. Okay. Okay. Any questions on this?
Yeah, really quick.
Sure. What's up?
Where did the X come from?
These, you mean these X's right here? Are the ones next to U1 and U2?
Yeah, the ones next to U1 and U2. Yeah.
Yeah, these ones came from, you know, it all came from this form right here. So the this x right here was kind of broken up into one u1 term and then another u2 term. And so this x right here basically got split into two terms because we had one with u1 and another with u2. Yeah.
Got it. Missed that X. Thanks.
Yep. Right. Okay, so let's talk about the shape functions a little bit more because these guys are going to be really important. Okay? And so first of all, let's compute the values of the shape functions at the boundaries. Okay. Okay. And so by the boundaries, what I mean is basically x1 and x2. Okay. Okay. And so we have n1 at x1 and n1 at x2. We're going to have n2 at x1 and n2 at x2. Okay. And so at x1, you know, if we plug in x1 for n1 right here, we can see that we get x1 minus x2 over x1 minus x2. And so this just gives us 1. Okay. But then if we plug in x2, what we get is x2 minus x2 over x1 minus x2, which is going to be 0. Okay. And then the opposite is going to be true for the other ones. Okay? So if we kind of draw, you know, what this actually looks like, is remember this these n1s and n2s are going to be linear functions, right? And so n1 will look like this. Okay, so this is going to be n1, and so it's going to start up at 1 at the at x1 right here, okay, and then go down to 0 at x2, and then the opposite is going to be true for n2. So n2 is going to look like this. Okay. Okay. And so that kind of solidifies its definition as an interpolation, because you know if we pick an x location that's closer to x1, then our solution is going to be more heavily weighted by u1. Okay? But then the opposite is going to be true for for location 2. So if we pick an x location that's closer to x2, then we're going to have a solution that's going to be more weighted by u2. Okay. Okay. And so one other useful form for this is to basically express this in vector form. Okay. Okay. And so we can say that ue of x is going to be n1 of x times u1 plus n2 of x u2. Okay. And so another way that we can express this is we can have a vector that looks like this. So we can have n1 of x, n2 of x. Okay. And then this is going to be multiplying u1 and u2. Okay. And so, you know, we've basically just taken our algebraic expression here and just expressed it in a vector. So if we perform the vector multiplication between these guys, we see that we get the same, you know, same algebraic expression. But, you know, the reason we're putting it in this form is so that, you know, once we plug this into the weak form, it'll make it easier to form our element stiffness matrix. Okay. Right. Any questions on this? Okay. All right, so one last thing that we're going to need before we plug this into our weak form is we're going to need some derivatives of this guy, right? Because remember in our weak forms, we had the derivative of our solution, okay? Okay. And so how do we express the derivative of our approximation or interpolation function? Well, it turns out it's actually pretty easy because, you know, if we assume that our nodal solution values u1 and u2 are constants, right? So they're just going to be whatever the solution value is at the nodes. When we take the derivatives, we actually only need to take derivatives of the shape functions. And so this is going to be equal to u1 dn1 dx plus u2 dn2 dx. Okay. And then again, you know, we can put this in vector form. Okay, so this is just going to be simply dn1 dx, dn2 dx. Okay, and it's multiplied by u1 and u2. Okay. All right. So I know there's a lot of vocab and stuff today, but one more. Okay, so this is often given the symbol B, E. Okay, so you might see this notation, in the textbooks or something. And so this BE right here, technically, for 1D cases, it just ends up being a vector. But once we get to 2D, this is actually going to be a matrix. Okay? And so this BE right here is called the strain displacement array. Okay. And in particular, for the 1D problem that we're going to consider with linear shape functions, it's given by the following. And so if we actually take the x derivatives of our shape functions, which is simple to do because it's just a linear function, we simply get the following. So we get 1 over x1 minus x2, comma, minus 1 over x1 minus x2. Okay. And just a little thing of notational simplicity. If we define L, this variable L right here, this to be the length of the element. Okay, where the length of the element is given by x1 minus x2. Another way that we can express this B vector right here is simply 1 over L, comma, minus 1 over L. Okay. And that'll let us basically simplify our notation just a little bit. Okay. All right, so now that we have the derivatives of our function right here and we have this B matrix, we're ready to start actually plugging this into the weak form and actually getting an element stiffness matrix out of this guy. Okay. All right, any other questions on this? Okay. Okay, and so that's everything with the shape functions and our approximation functions. And so now let's plug this in. Okay? And so from these, we'll finally be able to form the finite element equations. And so, like mentioned before, our starting point will be the weak form. So let me write it down again, just to kind of refresh your memory. Okay, so we have an integral over the entire domain. So this is 0 to big L. So big L is different from little l. So little l is just the length of just one element. Big L is going to be the length of our entire domain. Okay. So let's do elasticity first. So we're going to multiply dw dx. Remember, w is our weighting function. Okay. And we're going to multiply that by the Young's modulus and the elasticity. And then we're going to multiply that by du dx. dx. Okay. And so this is going to be equal to integral from 0 to L of w of x, b of x, okay, dx, plus our Neumann boundaries. So this is going to be w dot a dot t bar, okay, and this is evaluated at our Neumann boundaries. Okay. Okay. And so this is just our straight up weak form right here. Okay. But remember, we're not solving the weak form over the entire domain. What we want to do instead is we want to solve this over all of our elements. Okay. Okay. And so we're going to leverage the fact that, if we have an integral that goes from 0 to L, we can break this up into a bunch of smaller integrals and then just simply add them together. Okay. And so mathematically it looks like this. Okay. So I'm just going to do this for this first integral, but it's also going to apply to the body force integral as well. Okay. Right. So if we have this integral from 0 to L of dw dx, e a du dx. dx, okay? This is going to be equal to, a bunch of integrals over all the other elements, okay? And so let's say that our first element goes from x1 to x2, okay? And we're going to have the same integrand, okay? Okay? And so this right here will be the integral over element 1. Okay? And then we have the same thing for element 2. So let's say that our element 2 goes from x2 to x3. Okay? Okay? And so this continues on, for as many elements that we have. Okay? So visually it looks like this. Okay? Right? So our original domain here goes from x is equal to 0 to x is equal to L. And so after we discretize it, it's going to look like this. Okay? And so I only have 2 elements pictured here. So, but you can imagine if we broke this up into more elements, we'd have more integrals right here. Okay? And so this kind of motivates, how we can actually, break up a situation like this and actually solve the same problem. Okay? And so again, we're leveraging the fact that we're performing an integral, and then with the integral, it becomes a lot easier to kind of break up our problem into a bunch of these different, pieces. Okay? And so all we have to do in order to solve the solution over the entire domain is to solve for the solution over each of the individual elements. Okay? So we want to evaluate this integral right here. Okay? And then once we do that, we can just simply add them all together, and that will give us our full solution. Okay? Right. And then just like we saw in the first half of the class, the output for this, or what we're eventually going to be solving for, is a vector of the nodal solution values. Okay? Okay. All right. All right. Any questions on this? Okay. And so breaking up the problem into this form will also give us, will also bring us to another familiar concept, is that evaluating each of these individual integrals will give us our element stiffness matrix. Okay. And so let's see how that's actually done. Okay. And so what I'm going to do is I'm going to take our weak form and then just evaluate that for a single element. Okay. Okay, so we have integral from x1 to x2, dw dx, e times a, du dx, okay, times dx, and this is equal to our body force term. Okay, so this is x1, x2, w of x, b of x, dx. Okay. And so I'm going to ignore the Neumann boundary condition for now, just because it's a little bit convenient that way. And then I'll show you how to bring it back in later. Okay. Okay. And so now that we have this form, what we need to do is we need to plug in our approximation functions for both u and w. Okay. Okay. And so, even though we're throwing in this new function w of x in here, we're going to use the same approximation. So we're going to use the same shape functions. Okay. And so what that means is that our w of x is going to be w1 n1 of x, okay, plus w2 n2 of x. Okay. And our u in this case is going to have the same form but with different values. Okay. Okay. And so since we have these derivative terms here, we're going to need the derivatives of this guy. And so this is going to be dw dx. Okay. Is going to be equal to w1 dn1 dx plus w2 dn2 dx. Okay. And du dx is going to be u1 dn1 dx plus u2 dn2 dx. Okay. All right. And so let's remember kind of you know, the fact that we can also put these in terms of vectors. Okay. And so one subtle thing that we're gonna do for the w's, just to make sure that we can get a good matrix, is we're gonna transpose this system. Okay. And so for w of x, what this is gonna look like is we're gonna make w1, w2 into our kind of our row vectors, and turn n1, n2 into column vectors. Okay. And we're gonna do the same thing for the you know, for the derivative. Okay. So dw dx is going to be w1 w2. Okay. dn1 dx dn2 dx. Okay. And so these are swapped from what they were for u, just because, you know, it makes for kind of a slightly better system. Okay. And so first thing I'm going to do is I'm going to plug in kind of the derivative values into the left-hand integral. So I'm going to take this guy and plug it in for here, and I'm going to take this guy and then plug it in for that, and then we're going to actually evaluate that guy out. Okay. All right. Any questions on this so far? Okay. Okay. So let's go ahead and plug those guys in. Right. And so I'm just evaluating the first integral first, just because it's going to be a lot to write down already. Okay. And so plugging in w of x, or approximation of wx, we get w1, w2, okay, multiplied by their shape function derivatives. Okay. Okay. And then we have the same things for u. Okay. Okay. And so all I did there was I basically plugged in the vector form approximations for w of x and for u of x. Okay. Okay. And so one thing that we can do at this point is, because w1, w2, u1, and u2 are constants. Okay. And so if they're constants, we can basically pull them out of the integral. Okay. And so if we do that on the left-hand side first, then we get w1, w2 outside of the integral. Okay. And then we get dn1 dx, dn2 dx, okay, times EA times dn1 dx, dn2 dx, okay, dx. And then this is going to be multiplied by u1, u2, which again, remember, we took these out of the integral, you know, just because they're constants. Okay. Okay. And so now what I want you guys to look at is basically this term, or this product in the middle right here. Okay. And so here on this side we have a 2x1 matrix, and then right here we have a 1x2. Okay. And so if we perform the matrix multiplication here, what we get is a 2x2 matrix. Okay. Okay. And so that's not a coincidence. And so that 2x2 matrix that we're going to get from this is going to be this is going to form the basis of our element stiffness matrix. Okay. So let me put a box around this. And so this integral expression right here, what we can do is we can basically plug in for dn1 dx and dn2 dx, and then by evaluating that integral, we're going to get our element stiffness matrix. Okay. So it was a very roundabout way, but we were able to kind of get our element stiffness matrix from this guy. Okay. All right. Any questions on this? I know it's kind of a lot of abstract math right now and just a lot of symbols, but once we do an example, I think it should become more clear. I don't think we're going to get to it today, but we'll probably get to the example on Wednesday. Okay. Okay, so that's the first integral. But remember, our weak form had the other integral too that involved the body force. Okay, so let's just simply let's just quickly derive that guy. And so we have integral from x1 to x2. And then we have w of x, b of x, okay, dx. Right, so let's go plug in. We don't have any u here, so we just have w. So let's just plug in for w here. And it's just simply w of x, not its derivative. And so if we do that, we get w1, w2. Right? Again, these are constants, so we can pull them out of the integral. x1, x2. Okay, multiply by the column vector n1, n2. Okay, b of x, dx. Okay. And then from here, what I'm going to do is I'm going to circle this guy. Okay. Because when we evaluate this guy, we take the integral of this. We're gonna end up with a 2×1 vector. Okay. And this 2×1 vector is something that's going to be important because this becomes part of our element forcing vector. So this concept is a little bit new. I mean, we've seen forcing vectors before, but we've only seen them within the context of our global system. Okay, but now because we have this additional body force, which we hadn't considered before, that's also going to produce loads and forces onto our model. Okay, and so the way that we're going to evaluate these is kind of on an element by element basis, right? And the way that we do that is we evaluate basically this additional integral, which is going to give us additional contributions to our forcing vector. Okay. Okay. And so that's the body force term. And so now what about our boundary conditions? Okay. In particular, what about our Neumann boundary conditions? Okay. And so remember, the thing about the weak form is that the Neumann boundary conditions are baked right into the expression for the weak form. But we haven't evaluated it yet because remember, we're doing things on an element by element basis. But remember, for the Neumann boundary conditions, these only are applied on the kind of the boundaries of our global model. Okay. Okay. And so, when we break this up, when we break up our domain into elements, we're going to have a lot of elements that don't even see a boundary at all, right? And so say that we have, a domain that looks like this, okay? We break it up into a bunch of elements, okay? If we consider, maybe this element that's in the middle right here, okay? This guy doesn't even know what a boundary is because it's not even close to one, okay? And so for these elements, that are on the interior, we're not going to evaluate any boundary condition terms just because it doesn't make any sense because it doesn't even see a boundary. And so when we're applying our Neumann boundary conditions, we can only apply them on the elements that border a Neumann boundary. And so what this means is that for the majority of elements, we're not even going to touch the Neumann boundary condition term. Okay, and so for the 1D case, at the very most, you can only have one Neumann boundary condition. So we're only going to evaluate this term for one element for our 1D case. Okay? So of course, for 2D, this blows up quite a bit. But because in the 1D case, we only have two boundaries. We just have the left and the right, and one of these has to be, at least one of these has to be a Dirichlet boundary. And so that means there's at most only one Neumann boundary for a 1D case. We're only going to apply this for that. Okay. And so if we write out the mathematics for this term, okay. And so remember, for this term, it looked like this. Okay. Okay. And so we had our weighting function multiplied by the area multiplied by our traction. Okay. And so if we plug in our approximation for W, it would look like this. Okay, so we have W1, W2, okay, N1, N2, okay, A T bar, okay, all right. And so we would only do this for the, for the elements at the boundary, okay. All right, so if you remember from our the first what we did before the midterm, our Neumann boundary conditions the way it made its contribution was through the forcing vector. Okay, and so now that we're doing these kind of boundary value problems, we have two contributions to the forcing vector. Okay, and so we're going to have one contribution from the body force term, and another contribution from the Neumann boundary, only for the elements where we're on a Neumann boundary. Okay? And so the combination of these two guys is going to be our element forcing vector, which we'll call Fe. Okay? Not to be confused with finite elements. This is little f and upper score. Okay. Okay. All right. Any questions on this? All right, so we're just about, wrapping up this derivation here, but let me just kind of, pull it all together. Okay? And so, what we did before this page was we derived an expression for the element stiffness matrix. Okay? And so if we call our element stiffness matrix KE, okay, we can basically combine it together with this. Okay? And so, our whole system will look like this, where we have W1, W2 times KE, okay, times U1, U2. This is going to be equal to W1, W2, okay, multiplied by Fe. Okay. Remember, Fe is the combination of our body forcing and also our Neumann boundary conditions. Okay. And so what we notice from this expression is that we have W1, W2 on both sides of our equation. Okay. And so what this means, and the fact that W1, W2 can't be equal to 0. And so what this means is that we can basically just cancel them out, okay? Which is nice because we don't care about the weighting function, right? We just kind of use it as kind of a stepping stone to get us to our finite element formulation, okay? And so if we eliminate the W1, W2, what we're left with is K, right, which is our element stiffness matrix, multiplied by U is equal to F, okay? All right, so first of all, don't read that backwards. And second of all, this should be a system that's very familiar with you, right? Yes, we have stiffness matrix. Okay. We have U, which is our solution vector. Okay. We have F, which is our forcing vector. Okay. Right, so this is the exact same form that we did, before the midterm, right? And so, we came about this in a very, very different way, but through this approximation and through these shape functions and all that stuff, we arrive finally at our linear system, which we can solve, we can assemble, we can solve just as we've done before. Okay. Okay. Any final questions on this? All right, so question. So is there a way to derive Hooke's law from the matrix products inverse T, K, T? So in these problems, we're not going to we don't actually have to do any kind of transformations because all the geometric information will be baked into naturally into the coordinates for the element. So that will be kind of be baked into kind of the shape function derivative. So we're not going to have to do any kind of transformations. We need kind of a transformation matrix like that. But you can actually take like a spring, you can actually take a spring problem and kind of, do this kind of same exercise. It's just that the weak form for a spring problem will look different. So instead of EA, I think you would just have K, spring constant in like this, right? And so you'd still be able to do a spring problem like this. It's just that the K would replace the E times A, and you derive it kind of the same thing. All right, any final questions on this? Okay, and so we're going to pick this up again on Wednesday. So on Wednesday, we're going to do an example to basically, put some concreteness to all this kind of abstract math, and you can kind of, you'll be able to see, how this is actually going to work out in practice. Okay, but that's it for today. So thank you guys, everyone, for tuning in. Have a great evening, and I'll see you on Wednesday. Thanks, guys.